students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself, Jaimin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with chapter number 1, which is the phase equilibria. So in this lecture, we are going to discuss about solid-liquid equilibrium, solid-vapor equilibrium, and binary liquid-liquid equilibrium diagram. So let's first start with solid-liquid equilibrium. Solid-liquid equilibrium data are obtained experimentally by cooling a liquid mixture of known composition and recording a temperature continuously function of time. A breakpoint in this curve indicates the formation of solid phase. The temperature at this point is a solid liquid equilibrium temperature, and the composition of liquid mixture gives solubility of solute in solvent. Solid liquid equilibrium data are generally present in form of temperature versus solubility. Phase diagram under the isobaric condition are obtained. Binary solid liquid equilibrium phase diagram can be classified as a system exhibit aquatic behavior and system forming a solid solution. So there are mainly two types of solid liquid equilibrium diagram: system exhibit aquatic behavior and system forming solid solution. So let's first discuss about solid exhibit aquatic behavior. Among the phase diagram exhibit aquatic behavior, the simplest one is shown in this figure. The temperature at point A and C represent freezing, or can say that melting temperature of pure component A and pure component B respectively. Only homogeneous liquid phase exists over the curve AEC. The curve AE represents liquid curve on which pure solid component 1 is in equilibrium with the liquid mixture. Similarly, the curve CE is a liquid curve on which pure solid component 2 is a equilibrium with the liquid mixture. In other words, while the curve AE can be regarded as a solubility curve of solid 1 in solvent 2, where curve CE represents solubility curve of solid 2 in solvent 1. Therefore, liquidious curve are determined from the solubility. The curve AE and CE intersect at point E, known as the aquatic point. The aquatic point, the liquid phase is a equilibrium with two solid phase. Since their composition are same, no separation is possible at that aquatic point. The corresponding aquatic temperature represents the minimum freezing, or can say that melting temperature of the mixture. Note that aquatic point is among these to all the azeotropic point in vapor liquid equilibrium. The curve BED represents solid curve below the which non-homogeneous two-phase solid consists of pure component 1 and component 2 where exists. Consider a mixture at point F as shown in this figure. As this liquid mixture is cool at constant pressure, pure solid component 1 form when the temperature drops to T star, or consider point G, and relationship between T star and X2 star is given by this equation. As the temperature is further decreased, pure solid component 1 continuously form and liquid mixture becomes richer in component 2. For example, at point H, the amount of solid 1 at liquid mixture can be calculated by the application of rule in form of amount of solid 1 upon amount of liquid mixture is equal to line HL upon line HK. So this is how we can calculate amount of solid component 1. Now let's discuss about the second system, which is a forming solid solution. The component of solid solution completely dissolve in one another in manner similar to liquid forming homogeneous solution. As a result, the system does not have aquatic point, and solid liquid phase diagram are shown in this figure. Reassemble the temperature composition diagram for vapor liquid mixture, or can say that VLE diagram is the same as this solid liquid diagram. The two phase region in middle of bubble point and dew point curve, there will be a solid and liquid are in equilibrium, where in liquid vapor equilibrium curve there will be a liquid plus vapor are equilibrium. Similarly, here solid and liquid are in equilibrium. So this system is the same behave as a liquid plus vapor equilibrium diagram. So this system is a for the, or can say that this figure is for the system exhibit aquatic point, where this is a aquatic point. Below this aquatic point there will be a mixture of solid 1 and solid 2. When if we are going to increase the temperature, solid will be a melt. So if a solid is going to melt, it's converted into the liquid. So at this region some amount of solid 1 is converted into the liquid, and solid 2, or can say that component 2 is converted in liquid. So there will be a mixture of small amount of component 1 and maximum amount of component 2 of liquid plus solid 1. Okay, because there will be a maximum solid 1 here compared to the component of solid 2. Similarly, here solid 2 present, and in liquid small amount of component 2 and large amount of component 1 is present in liquid phase. So here liquid plus solid are in equilibrium. Here liquid plus solid component 2 are in equilibrium. This point is known as the aquatic point. Here its same behavior as the azeotropic point. We cannot separate from this point. So at this point there will be a three phase solid 1 plus solid 2 plus liquid phase. Okay, and this all above this curve there will be a liquid phase. So this is how solid liquid equilibrium exhibiting aquatic behavior. Now let's discuss about the system forming a solid solution. System forming a solid solution that can be represented by this graph, which is the same as a VLE graph. If we are going to hit the solid, it will be converted into the liquid. So there will be liquid plus solid are in equilibrium. If we are again going to hit that solid, it will all the solid converted into the liquid. So above this point there will be a liquid, below this point there will be a solid, and between these two curves there will be liquid plus solid are in equilibrium. And this is a tie line from which we can uh, represent various data of solid liquid equilibrium. So this is how solid liquid equilibrium works. Now let's discuss about the solid vapor equilibrium. When the solid is directly converted into the vapor, it is known as a sublimation. And if vapor is directly converted into the solid, it's known as a deposition. So this is a sublimation line where solid is directly converted into the vapor and vapor can directly convert into the solid. So this is how the solid vapor equilibrium is exhibited. Now let's discuss about the binary liquid-liquid equilibrium. When two liquids are only partially miscible, the equilibrium can be represented on rectangular coordinate as shown in this figure. A dome-shaped region is formed by the mutual solubility curve. Within a dome shape, the mixture exists as a two-phase. A composition of the equilibrium phase lies at end of the horizontal line at given temperature. For example, mixture M in this figure will separate into two equilibrium phase A and B. The relative amount of phase are given by the inverse level rule. So that can be given by amount of phase A upon amount of phase B is equal to line MB upon line AM. The point P gives the critical solution temperature outside the dome. The mixture is a homogeneous. So this is a homogeneous phase above and can say that outside of this phase there will be a homogeneous phase. This is a B rich phase. So this side is a B rich phase and this side is the A rich phase. And above this homogeneous phase. But in this dome side there will be a component A and component B are mixed with each other, or can say that mixture of two immiscible liquid phase. And this point P gives a critical solution temperature. Outside of dome there will be a homogeneous phase. So this is all about the liquid-liquid equilibrium for the binary mixture. We will discuss about the ternary equilibrium diagram for the liquid-liquid equilibrium in next lecture. So in this lecture, discuss about the solid-liquid equilibrium, then discuss about the solid-vapor equilibrium and liquid-liquid equilibrium for the binary mixture. This is a tie line in liquid-liquid equilibrium from which we can relate various data. So in solid liquid equilibrium there will be a two types, one with a aquatic point and second with a non-aquatic point, or which look like same as a VLE. Okay, so this figure represent the system exhibit aquatic point. This both figures is known as a system exhibit at aquatic point, and this figure is known as a behavior for the simple solid liquid equilibrium, which look like the vapor liquid equilibrium. Then again discuss about the solid vapor equilibrium. When the solid is directly converted into the vapor is known as the sublimation. When the vapor is directly converted into the solid is known as the deposition, or can also say that desublimation, and this line is known as the sublimation line. So below this temperature, the solid and vapor can be a equilibrium with each other. So this is for the single component. And then for the liquid-liquid equilibrium for the binary mixture, that can be represented by this dome type of curve. We can also represent this curve like this for the lower temperature, or can say that freezing temperature. And if we are connecting this both curve, then it look like this. Okay, so this becomes upper critical temperature and this becomes lower critical temperature. So this is point A, this is point B, this is component A and B. Here also this is component A and B. This is a homogeneous solution, and above this homogeneous solution, this side is A rich phase, this both side, and this both side is B rich phase, or considered component B rich phase. So this is how binary liquid-liquid diagram is a work. So this is all about today's lecture. I am completing my lecture here. Thank you.